All right, so this next example is one that appears in your book, and I'm using this one again because I want to use the picture of the phase portrait that they include in there. So it's a 2x2 system this time. We start the same way as before. We want to find the determinant of a minus lambda I to get the eigenvalues or eigenvalue for this matrix. In this case, that's going to look like 3 minus lambda, negative 18, to negative 9 minus lambda. Oops, I just want straight line. Okay, that's equal to 3 minus lambda times negative 9 minus lambda minus negative 36, so plus 36. This is equal to, if I multiply this out, I'm going to get lambda squared. Let's see, that's negative 3 plus 9, that's plus 6 lambda. And then 3 times negative 9 is negative 27, plus 36 would be plus 9. This is the same thing as lambda plus 3 squared. Setting that equal to 0 gives me an eigenvalue of negative 3, but with a multiplicity of 2. Okay, now we're going to attempt to find eigenvectors. So we go back to our matrix, this one in particular, before making it into a determinant, plug negative 3 in for our lambdas, and I'm going to use an augmented matrix like in my last example when I'm dealing with this. So 3 minus negative 3 would be 6. I have negative 18, 2, negative 9 minus negative 3 would be negative 6. And I use the vector 0, 0. This is how I find an eigenvector. Okay. Now, these two equations are going to end up being equivalent, so we're going to end up with infinitely many solutions like we have been. So I'm going to use this bottom equation. It's a little bit simpler. That bottom equation is the same thing as 2k1 minus 6k2 equals 0. Okay. Now I'm gonna isolate the k2 or the k1 here, so I can add that over, divide by 2. I get k1 equals 3k2. So if I set k2 equal to 1, then k1 is going to equal 3. 3 times 1. So I can use 3, 1 as an eigenvector in this case. Okay, so that's great. I have that now. However, that's the only eigenvector I'm going to be able to find. So I'm in that case where I have to come up with a second solution to my system of equations here, using this eigenvector somehow, and that's where we come up with that vector p. We do it in the same way that we did in the previous example. I use the same augmented matrix here, but I'm going to replace this last column with k now. So this is going to look like 6, 2, negative 18, negative 6, and then I'm going to have 3, 1 here. Okay? And once again, these two equations are going to be equivalent to each other, so I can use either one. I'm going to use the bottom equation again, which looks like 2, let's call these p. p1 minus 6 p2 equals 1 now. So this time if I want to solve for p1, I'm going to get p1 equals 1 plus 6, or sorry, I have to divide by 2, so this is going to be 1/2 plus 6 halves, so that's 3. Let's call that 3. P2. It's a little bit messy, sorry. I could set P2 equal to 1 if I wanted to. In fact, I could even set it equal to 0, which might even be easier. So if I set P2 equal to 0, this becomes 1/2 plus 0, so that P1 is equal to 1/2. And I did say before that we try to avoid fractions in eigenvectors if possible. Sometimes you can't. So this is one example where we're not really going to be able to do that. But P is now going to equal 1/2 0. That's the eigenvector I'm going to use here. Okay? So the theorem that we talked about would say that our solution to this, x, is equal to that x1 that we would have found, c1 times x1, where x1 is this eigenvector here, 3, 1, times the exponential using our eigenvalue, which was negative 3 in the exponent, negative 3t, plus c2 times k, which is 3, 1, times t, plus p, which we found to be 1/2, 0, all times e to the negative 3t. That would be our general solution, okay? So that's another example with repeated real roots. Here's what we have now for phase portrait. When we looked at the phase portrait, when we had two distinct real roots, we had two lines, which we really thought of as 4 half lines. Because we only have one eigenvector to work with, the eigenvector 3, 1, we can only get one of those lines in this case. But the blue curves, we arrive at those in the same way as before. We go to our solution, we plug in different values for these parameters, C1 and C2, graph the curves that would correspond to those parametric equations represented by that vector there. And you get a bunch of these kind of these curves that you're seeing here in blue. In this case, we can go through the same analysis as before, but we had one eigenvalue in our case, and it was negative. And when that eigenvalue is negative, you can see that on the red line, our arrows are pointing toward the origin, and that's because these blue curves are moving towards the origin. If you follow a particle along either of these curves, that's where it's moving towards. So when an eigenvalue is negative, or a single repeated eigenvalue, if it's negative, then the origin becomes an attractor. Alternatively, if the one eigenvalue, the single repeated eigenvalue that you're able to find, is positive, then the origin would be a repeller in that case, okay? And we're not walking through a lengthy argument as to why that is. It's just kind of making a note of that. Our third case deals with complex eigenvalues. Now, your book does a much longer derivation of this result than I'm going to do. And I'm skipping that derivation for a couple of reasons. One is it's very long, and this is already a long section, so it's partially to kind of save time. But not only that, the argument itself is actually, in essence, the same argument that we make when we talk about complex eigenvalues back in section, or not, complex solutions to your auxiliary equation back in section 4.3. So way back then, when we weren't talking about systems of equations, we're just talking about homogeneous linear equations with constant coefficients. We talked about how if your auxiliary equation has complex solutions, there's this whole argument you can go through to show that your solutions will take a form similar to what we're seeing here. Linear combinations of a cosine and a sine, where the beta that's appearing here is the imaginary part of your solution, and then that's all multiplied to e to the alpha t, where alpha is the real part of that solution. The only difference here is that instead of linear combinations where you have constants here and here, we're going to have these vectors, b1 and b2. Okay, and notice we're getting two solutions here where there's a plus in one case and a minus in the other. But the argument that helps us arrive at this solution, and I'll talk about what B1 and B2 are here in just a second, the argument that gets us to this point that your book walks through is in essence the same argument that's used in chapter 4. There's new notation introduced here for matrices, so we talk about what a conjugate matrix is and stuff like that, but the underlying math is essentially the same. So since you've seen that argument before, I don't want to walk through all of it here. We're just going to jump to the theorem that's important for our purposes and then talk about how to use it in an example. So here's kind of what we do need to talk about. Let's suppose that you're solving, again, a system of equations using eigenvalues and eigenvectors. You find an eigenvector of your matrix A corresponding to an eigenvalue, which happens to be a complex number, alpha plus beta I, okay? We're going to define this notation, Re of K1, to be the matrix that's the same size as K1, whose entries are just the real parts of K1. And similarly, Im K1, we define that to be also a matrix the same size as K1, but its entries are the imaginary parts of K1. Okay, then to give you an example, let's suppose K1 is equal to this matrix here, 1 plus 5i, negative 4i. The real part of K1 is the matrix whose entries are the real parts of these two entries here. The real part is 1 in this case and 0 in the second entry, so 1, 0. The imaginary parts of these entries are 5 and negative 4, so 5, negative 4. That would be the imaginary part of the matrix K1, okay? For the theorem that we're going to talk about here, which I kind of already talked about, we're going to set the matrix B1 equal to the real part of K1, and B2 will be set equal to the imaginary part of K1. That's the B1 and the B2 that are appearing here. Okay, and again, there is a lengthy argument that we can make to arrive at this. There's even a theorem that comes before this that's used in proving this, and we're opting out of going through all of that. I really just want to do an example to show you how this works. So one last example for this section. We want to solve this system right here. Notice it's an IVP. We have an initial condition to worry about. And this is also the example that's shown in your book. I want to use the phase portrait again. So the way we get an eigenvalue is the same as before. Determinant of a minus lambda I equals 0. That means that we're looking at 2 minus lambda, 8, negative 1, negative 2 minus lambda. Okay, this is equal to 2 minus lambda times negative 2 minus lambda minus 8, negative 8, so plus 8. Okay, this is equal to lambda squared. That's negative 2 lambda, positive 2 lambda, those cancel out, and then I get minus 4 plus 8. That's the same thing as lambda squared plus 4 equals 0. Okay, that implies that lambda is equal to plus or minus 4i, so two complex solutions. Now, remember, when you're solving a polynomial equation where all of the coefficients are real, then anytime you get a complex solution to that, it'll always come with a conjugate pair. So if 4i is one of our solutions, then negative 4i would have to be another one. And when we're dealing with these conjugates, the eigenvector that we're going to find only really requires us to pick one of these. So I'm going to go with the positive and set lambda equal to 4i. Okay? What does the system of equations associated with this look like? I'm actually not going to use my augmented matrix notation this time. I'm just going to use... I need to fix something. Not 4i, it would be 2i, wouldn't it? Glad I caught that. Okay. So what would the system of equations look like? Well, here's what the coefficients would look like. And I'm trying to find the matrix K here. So I'm going to have 2 minus lambda, which is 2i in this case. That should be 2 right there. 2 minus 2i times k1 plus 8 times k2 equals 0. And negative 1 times k1, so negative k1, plus negative 2 minus 2i k2 equals 0. Okay? You can show, as we've done before, that these two equations are equivalent and we can just solve one of them. So I'm going to use the second equation since that's the simpler of the two. If I added k1 to both sides, notice this says that k1 is equal to negative 2 minus 2i k2. So we can pick a value for k2 and then find a corresponding value for k1 to come up with our eigenvector. I could set k2 equal to 1. I'm going to choose negative 1 so that I can turn these negatives into positives just to make it a little bit simpler. So that means that my vector k is equal to negative 1 is k2. k1 would be positive 2 plus 2i. Okay? Now, in order to come up with our solution, we need those vectors b1 and b2. So remember, b1 is the vector containing the real parts of our eigenvector. So that would be 2, -1. And b2 would be equal to the vector containing the imaginary parts, 2, 0. Okay, now we're going to come back here and take a look at what our solution is supposed to look like. b1 cosine beta t minus b2 sine beta t. Notice for the second solution here, the b2 and the b1 switch places. So b2 is going to be the coefficient on cosine, b1 the coefficient on my sine. So using that, our solution is going to look like this. X equals c1 times b1, which is 2, -1, cosine of beta. And beta in this case is 2. Remember, that's the imaginary part of our eigenvalue. So 2t minus b2, which is 2, 0, sine of 2t, times the exponential e to the what t? Well, e to the alpha t, but alpha in this case is 0 because that's the real part of our eigenvalue here. So e to the 0 is just 1, and we don't need to write anything additional for that. Plus c2 times, remember, this is where the eigenvectors, or the vectors trade places, b1 and b2 trade places. So I use b2 first, 2, 0, cosine of 2t. My minus becomes a plus here, and then I get b1 to -1 sine of 2t. Okay, now remember, that's not my solution because it's an IVP, so I need to use my initial condition here. X not equals 2, 1, or x of 0 equals 2, 1. This means that the vector 2, 1 is equal to what? Well, when I plug a 0 in for t, both of the sine terms are going to become 0s. Those go away. My cosine terms become 1, and so I get c1 times 2, -1. And sorry, that's supposed to be negative there. Plus c2 times 2, 0. Now, I could solve that like a system of equations, but if you notice, the vector 2, -1 is already showing up right here, and that's what I want this expression to equal. So it would make sense to want to plug a 0 in for c2 to get rid of that term completely, and a 1 in for c1 to make this side equal to the vector 2, -1. So sometimes we get equations like this that are easy to solve by inspection. This implies that c1 equals 1, and c2 equals 0. So now I just need to plug those back in up here. If c2 equals 0, I get to lose all of that. If c1 is equal to 1, I just get what's inside parentheses here. My solution is this. 2, -1 cosine of 2t minus 2, 0 sine of 2t. And that's it. Okay? In this case, we could also draw a phase portrait. Notice I don't have any lines, any guiding red lines like in the previous two phase portraits we looked at. And the reason for that is because we're plotting this in the real plane, in the xy plane. And my eigenvector that I came up with had a complex component to it, a complex entry. So I can't draw that in the real plane. So I don't have any vectors that I can put lines through. However, if we just go to our general solution up here and pick different values of C1 and C2 and plot, or graph the corresponding curves that we would get, we get a lot of these kind of elliptical looking curves. The one in red here is the specific solution that we came up with for our IVP. And you can see that it passes through the point 2, -1, which our initial condition implied had to be a point on our curve. Okay? So it's a long section, but we're finally done with 8.2.